Okay, good morning again. I know that most of you already tired from 1 hour of speeches, so I try to be reasonably short and try not to give too scientific formulas or nothing really, which if you have a university degree, I'm pretty sure you will be able to follow my presentation. I'm sorry for not being able to speak Portuguese, but I guess most people know. So when someone receives an honorary degree or even a higher prize like the Nobel Prize, usually two questions come to mind. Okay, how this guy managed to do this? Okay, and why this Nobel Prize, why this guy, not myself, and so on. So I try to answer those two questions. First, I'll tell the story behind this discovery, and then explain why, what's so special about graphene, why you now have McGrath Institute in this campus. As was mentioned before, somewhere a short 20 years ago, 1994, I got my first tenure position, so safe academic environment, no one going to fire you, and so on. So usually most people get relaxed doing their teaching, research, administration, and so on. A kind of youth and adventure has gone from the lives, but I was too young for that at the age of 35. There was too much adrenaline still in my blood, so I thought, if I'm so secure in my life position, okay, I'm still not paid good enough to do this routine. Let's do something interesting. Let's do something for my soul rather than for my salary. So, and I started doing some random experiments, okay, which is completely out of my line of research for what I'm paid, given grants, supported by governments and universities and so on. So just, just for fun. Maybe after a few beers at Friday night, okay, we start doing these experiments. But on the background of all those experiments, there was something, okay, background knowledge, because you're educated, you have a lot of knowledge. Even the random experiments are not so random at the end. So at that time, I was working in Nijmegen, it's in the Netherlands, and we had ancient magnets, which look like that. It's a huge machine, actually, and they were around probably for 50 years in different parts of the world, so not very nice to work with. And for my line of research, and most people's lines of research, it's require some extra equipment, and it all gets very, very scientific at the end, and uncomfortable to work. And it requires an energy probably as much as powers the whole University of Mackenzie, and you can run them only at night. No one knew what to do with those machines. As usually happens in scientific world, people say we can't live without those machines, but a few years later they start thinking, okay, what we really can do with those machines, and I was in charge of those. So I heard at that time about a phenomenon called magnetic water. Probably some of you in the audience heard about magnetic water. The idea is that you put a small magnets on top of your water taps, and calcination, this scale which covers your hot kettle, disappears. I didn't know much about this magnetic water, but I thought, why wouldn't we just for fun try to put water inside these high magnetic fields, probably no one have tried this before without thinking much about this, and this is not the way usually science done. People do not pour water inside their expensive equipment, but once upon a time, we just took a bottle of water and poured water inside without, if you ask me why, I don't know why I did it, okay, yeah, but I expected to water end up on the floor, as any reasonable person would expect. There is a mess with the slides somehow, but that's 2 slides shows what people knew before. It's this calcination which allegedly disappears if you put water in reasonably small magnetic fields of fridge magnets and so on. So scientifically, I still have nothing contributing to this phenomena of magnetic water, but what we observed, instead of water ending up on the floor, it starts levitating somewhere here inside this magnet. You're looking from the top, and somewhere here this droplet of water appears. Actually, those balls sometimes like tennis balls, quite big, and I love to watch this, okay, and I think it's, when you watch it, it's kind of making you relax. This is the most important outcome of this experiment, turned out to be therapeutical, okay, because although I didn't believe my eyes when I saw it, it took me probably 20 minutes to realize that phenomena behind is diamagnetism. So you know magnetism about iron, paper clips, fridge magnets, and so on, but you, myself, paper, plastic, wood, everything around us is magnetic as well. It's very tiny magnetism, 1 part per million with respect to, say, magnetism of copper, of iron. And most people, and most scientists, most importantly, always assume that it's so weak and feeble that you really need some special scientific setup to test this phenomena. But you see, the magnets which we employed in these experiments were only a couple of times larger than the magnetic field you say in imaging. If you go in a hospital, hopefully not, but those scanners, magnetic scanners used in the hospitals, they use magnetic fields comparable in strength which we have used before. So in those magnetic fields, quite dramatic phenomena with seemingly non-magnetic things can happen. So the problem was, I would leave this experiment as it is. It's fun, it's interesting, therapeutic, as I mentioned before, but then my colleagues, professionally working with high magnetic fields for decades, start saying, you're pulling our legs. I told them in the morning, okay, that water levitates, everything levitates. No one believed me. And there was a long queue of people who came sometimes from different cities, from different countries, to be sure that it's indeed. And the rumor came across, and many people came around, and they have, with their brilliant ideas, what else we can put inside magnetic fields. We put wine, water, different vegetables, and so on, and people continue coming and coming and coming. So at some moment it turns out to be important to show something not only my colleagues could appreciate, but students, school children, and so on, so they could appreciate that we're magnetic as well, that magnetism, diamagnetism, this subtle phenomena, is not as subtle as we assume after all. In the meantime, I had a lot of fun with colleagues, still trying to appreciate that diamagnetism is very important. This is an example of myself trying to prove you that I'm not a typical boring academic. Sorry, many people in the audience are. So this is an example of a paper which I published. Ignore the title, ignore the journal. What you have to focus on this name. It's read hamster Tisha. So official name dwarf hamster. We call this, okay, sounds Russian a little bit. Nickname Tisha, and the job levitator. And he contributed firsthand in those experiments, and he safely levitates inside the magnet. Unfortunately, I don't have movie or a picture inside, because this is the tiniest hamster, dwarf hamster I could find, but it still was pretty big for the magnet. So when it was put inside, it started climbing outside and filled the whole hole. So people sometimes ask why I put the hamster inside. Why did I do this experiment? And my usually reply is that I found him much smarter than some of my students, and he helped me in those experiments much more than many of my colleagues. But hamster was too big, so there was the need to relate to people outside the scientific community to see what's going on, and eventually we found a candidate. Frogs can be very tiny, and I put a frog inside. It probably was the hardest experiment I have ever done in my life, which is actually true, because as a physicist, I'm used to deal with dead objects, and frogs, they stick to your fingers, they jump, they don't want to be in the precise position where you try to put them inside the magnet. And it was pretty hard experiment, but eventually we managed to make a few seconds of movie where you see that the frog is alive and so on. And if there are animal rights activists in this audience, let me assure you that the frog was fine and eventually was returned to the biology department. But to finish this part of my story on a serious note, okay, whether these experiments were worthwhile, because it was not a scientific discovery, phenomenon behind these experiments, okay, was already known for hundreds of years, but sometimes I go in the conferences and people still meet me and say, look, I don't know anything about graphene, but I give lectures about magnetism, and I always start my lectures with this picture of the frogs, because people immediately get quiet, students, and like to learn how the frog can fly, and at least one of my lectures gets successful and people listen to me. So it's in many textbooks, but for me the most rewarding was a letter I received about, nearly 20 years ago. The letter reads, the frog to float, more information. I'm 9 years old and I want to become a scientist. With this letter, I rest my case of defending my frog experiments and my Ig Nobel Prize. But, when you learn to do something out of the ordinary, it's very hard, like riding a bicycle, it's very hard to forget. You always try to look for something outside your area of research. And after many unsuccessful attempts to reproduce the success of frog or similar experiments. I stumble on something rather, why it's not plain? Yeah. Rather remarkable animal. Of course, you know geckos, and they can stick to glass ceilings and so on, and it's beautiful slow motion. But for me as a scientist, I learn the mechanism behind this climbing ability, and the mechanism is quite simple. Toes of geckos are covered with tiny, tiny hairs. When you have a match or take one of your hairs and put it against, say, a piece of glass or another surface, there is a force which is called van der Waals force, which is attractive force. It acts between anything you can touch. You do not notice this force. Again, it's very tiny, minute force, nanonewton force. But geckos utilize this force. They have billions of hairs which attach at the same time to the opposite surface. So you have billion times nanonewtons. At the end, you get a quite formidable force, about 1 Newton, which is strong enough to provide geckos with this climbing ability. Another shocking for me discovery at that time, it was about 10 years ago, 12 years ago, was that the size of geckos' hairs, they're much smaller than hairs on your hairs. They're tiny, 10 times, 20 times thinner than a typical hair. This is the same spatial scale I normally do in my professional work, which I skip from this presentation. So the immediate idea, why wouldn't we try to use our facilities to reproduce those gecko hairs? Why no one has done this before, I don't know. In a sense, this also work which was not funded by anyone. It was at the spur of the moment, trying to do something which I normally wouldn't do, and I had any funding to do. But we eventually managed to make a small piece of this gecko type hairs. Now it's called gecko tape. It's a forest of polymer columns. You see here they are not as dense as gecko hairs, and they cluster a little bit, but I wanted to make a very big piece, but the amount was only enough for putting a toy. When I apply for a funding to get a gecko glove to put one of our students out of the window and show that it's possible to make those gecko gloves, eventually, the story faded away, but it continues to be this paper is cited 1,000 times. It continues to be a very important part of research on adhesives. We still don't have gecko gloves around. The problem is that, but I saw people hanging from a ceiling on kind of gecko gloves, basically the same material. The problem is that geckos can clean their hairs. We don't know how they do this, but they clean those hairs. Our gecko gloves are good for 1-2 attachments, and after that everything becomes clogged and dusty. How geckos can clean this self-cleansing mechanism is still remains to be understood, and only after that we can hope for real commercial products. This brings me to the next part of my story, which is related to the subject of yesterday Open Center. the subject is graphene. So again, I checked my previous publications before, say, 2003, and I never in anyone mentioned a word carbon or graphite or anything like that. So it was out of my main direction of the research, and the idea was the following. People were so excited about carbon nanotubes, and I was envying them. It's such a remarkable, at that time, material carbon nanotubes were. So I thought to do something similar but different. And I also knew that thin films of graphite are impossible to make. And the reason is this material has the highest melting temperatures, 3,500 centigrades. This is why iron is always made melted on, or whatever, gold in graphite crucibles and so on. So I was tinkering with the idea of how to make something which would be interesting to measure, very thin films of graphite. So we didn't have those chunks of graphite, but we get in our lab, we use so-called highly oriented pyrolytic graphite, which is used routinely for many decades, probably many centuries, in different labs around the world, and for many decades it was a material. If you have so-called atomic force microscope or any other atomic resolution technique in your lab, you use this material for calibration. How people usually do, they put this material gets after a few minutes, it gets absorbed water, hydrocarbons on the surface, so people put a scotch tape on top and peel the surface layer, revealing the clean graphite surface, and then put this material inside their scientific equipment. The scotch tape, which peels the top dirty layer, gets into a litter bin. And what we have done, we looked at what is left on the tape, and this is an image what you have on the tape after you press it against any graphite material, and you'll see a lot of black spots, some rubbish on the surface, and people obviously throw this tape away without knowing that together with the tape they possibly throwing away their Nobel Prizes. So the difference was that I put this tape under the microscope and have seen that some of those pieces, although small, they are transparent. It's a metal, and metal usually non-transparent. When something is transparent, it tells you that it's really, really thin. And although the size is small, it's big enough for our lab to study properties of this material. So for me, it was kind of a eureka moment at that time, because I thought, wow, we get very, very thin metal. It should be interesting, and particularly this metal refers to carbon nanotubes, a very popular subject at that time, as I mentioned. So, but more importantly, with the previous knowledge, I realized it's not just junk on the surface, because there is something much more fundamental going on. When we're looking around yourself, everything around us has 3 dimensions: length, height, width. You won't find materials in our 3-dimensional world where one of these, say, thickness is essentially absent. And there is a very fundamental argument that this is impossible to occur in nature. For example, everything comes from, I don't know, melt or grows. Essentially, in order to merge individual molecules and atoms which present in space together, you need temperature. Temperature allows them collide and stick together. At zero temperature, in a cosmic cold, no reaction happening. And the temperature, random movements try to destroy the order. And initially you might find some flat pieces, but then you put more and more molecules into this box and try to grow, and everything gets a three-dimensional shape. Because nature is smart. Nature knows we are living in 3 dimensions, while I will be using only 2 or 1 of those. Let's try utilize those 3 dimensionals. It's more stable structures in this one. That's how the nature thinks, but the humankind is a bit smarter than that. So if nature does not allow this, we can still do something artificially. So you can take a normal crystal, let it be cooking salt. We know that crystals contain rows and planes and so on. And you can imagine, say, Gedanken experiments that you take very small tweezers and pull out one of the planes is pulled out from these crystals. If you can do this experiment at lower temperatures, not at temperature of the growth, but at room temperature, then you may hope that this plane will remain intact, because the growth occurs at very high temperature, and now you're doing this extraction of the plane at lower temperature. So this is what we essentially done in those Scotch tape experiments, and this is an example. What you see here on by your naked eye, it looks probably not a good contrast here, but there is a 1 millimeter layer on top of some substrate, and this layer is a single 1 atom thick material, a layer of carbon atoms, and probably there are very few defects. At least no one has found any defects in this kind of the system. So it's a new kind of materials which we have not been aware before, materials which are 1 atom or 1 molecule thick. So this is all good and sounds very scientific, and initially it would be a point of curiosity, because the structure, we know how the structure should look like for this material. It's extremely simple, and you do not expect much from this simple structure, no complex phenomena and so on. So it would remain kind of known for not many physicists and scientists as a material, but what we have started, not just declaring that we have managed to create a material which is 1 atom thick, the thinnest imaginable material before, we start learning properties of this material. So those properties tend to be absolutely wonderful. This material attracted more superlatives than any material in the world, as far as I'm aware. So those properties is, of course, it has the largest surface area than any other material because of this thinnest. It's stronger than even diamond. Of course, you have to remember that this material is very thin, but it's the strongest material measured. It's stiffest material. It's stiffer than anything we know. At the same time, despite being stiff, it allows to bend it and stretch it. You can stretch this material by 10%, like rubber. At the same time, it's stiffer than diamond. Try to do something like that with a diamond. It cracks. And it conducts heat better than any other material. It shows wonderful electronic properties. It's completely impermeable to anything we know. And there is a lot of other properties, as I mentioned before. There is not enough space on this page in order to list all those superlatives. So in a sense, it's not myself who got the Nobel Prize, it's this material for its remarkable properties got the Nobel Prize because they were out of what one can possibly expect to any material. So step by step, we learn about those properties within, say, 10 years. We now more or less know everything about this material. So the problem is now to find how to use those properties for something useful for the humankind. But I was personally involved in studying electronic properties of this material, why this material allows electrons move freely than, say, in copper or in gold, why it's much more conductive than anything we know. It's a rather complicated story, but and it's the most probably scientifically valued story about its electronic properties. So I compressed everything in one transparency, trying to give you an idea of what's going on without too much scientific jargon. Essentially, when we are dealing with properties of electronic properties of material, why they conduct electricity, why silicon behaves this way and gold or copper behaves different way, we use so-called Schrödinger equation, which is on the top, and this is it. This is can get very complicated, but this is the basic equation which explains electronic properties of those materials, why our computers work, and why our mobile phones are operational. You probably hear sometimes news from particle physics community about astrophysicists and so on. They have their favorite equation, which is called Dirac equation, which explains properties of the matter when it's moving at very high speeds, close to the speed of light. And this is, again, relatively, in the first approximation, relatively simple equation. What graphene brought to us, it brought us a material which is this column, which is a single layer of atoms, which is explained by equation, where you have to explain properties by equation, which is quite similar to the equation used in particle physics. And if you put two layers of graphene equation, you get a mixture of this equation with another equation. You can imagine our way of learning things about nature expanded twice. And you don't need to use particle accelerators to do this. In a piece of graphene, you can learn a little bit more about science than in a very complex experiment. This, again, sounded probably a bit too weird and scientific, but let me give you an example how unusual electronic properties of this material is. You know what happens when you drive your car into the wall, okay? Yeah, that's the outcome we're all familiar with, because we live in a macroscopic world. If you would be a billion times smaller and lived in a quantum world, which, again, very important for our technology, in quantum world, you probably heard weird phenomena can happen. The car which drives into a wall doesn't completely stop by the wall, but a phenomenon called tunneling occurs. Part of the car goes through the barrier, part doesn't go through. I don't want to explain this phenomena because this is university textbook phenomena, and you heard about a strange quantum physics, duality between matter and etc., all related to this weird world. But the quantum world in which electrons live in graphene, even more weird than that. If you would live in a universe which behaves the same as electrons in graphene and build up a graphene car and try to build a barrier however high and however wide you build this barrier. Your car goes through any barrier without anything left behind. This phenomenon is known for 70 years, and no one even dared to test this phenomena in particle physics experiment because you really need to build barriers and accelerate it. People thought this phenomena should exist, but never even tried to probe this. Graphene is one of many phenomena, and people at this university, who associated with this university, has been heavily involved with studying one of those many weird phenomena which happens in graphene. Another example how interesting physics behind science of this phenomena, of this material, is the following. Okay, this experiment comes from about 8 years ago. At that time, there was a problem to make big pieces of graphene. With me, I always carry a piece of graphene on a plastic, just in case someone asks how it looks like. And this is how it looks like 10 years ago. You make an aperture and cover this aperture partially with graphene. This is light goes through, but you see weak contrast here, and when two layers, the contrast increases. So this material absorbs some light. So as a scientist, you like to analyze how much light it absorbs, and it turned out to be reasonably easy to do. You take a photograph and put it in a computer and figure out that it's 2.3%. And the material is gray material, absorbs equally at all those lines. For a layman, 2.3% doesn't mean much, but for a scientist, 2.3% with a bit of theory gives you an idea of what it is. Essentially, what we measure in this experiment, the fine structure constant. You probably heard about this constant, 1/137. Most mysterious constant in our universe. No one knows why this number is, why it's not any other number. So we really don't know what it is, but what is interesting when you have a piece of this material and look at this piece of material, you figure out that you, by your naked eye, probe this the most mysterious constant in our universe. So if you ever get some gadget like a computer screen or mobile phone, some of them I have seen some mobile phones with graphene. Remember that at the same time you are dealing with one of the most big mysteries in our science. Something probably more understandable, but again, my last example, how unusual the material is. Many other groups provided many other examples how wonderful it is, but this is what has been done in our lab. So we learned from our group that this material is completely non-transparent. And we thought, oh, that's a great idea. If it's completely non-transparent, then why wouldn't we put a stack of many those layers, which is easy to make, unlike single layer. It's much easier to deal with macroscopic pieces of the material. There is so-called laminates of graphene, very easy to make, very easy to deal with that. And we expected that this material would be, if one layer is not transparent, that many layers certainly shouldn't be transparent. So we take the most permeable gas you can imagine, it's helium, make a bottle, fill it with helium, and instead of cork, we use this very thin, 100 nanometers, 100 times thinner than the thickness of your hair, film to seal it. And of course, as we expected, we found that helium does go through. Was not surprised. So far, so good, and we tried many, many different materials to test the same way until we came across with water. And with water, we found that water goes through this laminate without any noticeable impedance. We thought for a long time that there was something wrong with the experiments and so on, but you can use the same film to seal helium or any other gas and then water and find out that water goes without any resistance. How can you explain this? It's eventually we explain. So the material is like not a continuous layer, but a laminate, many layers put on top of another, and there is a kind of a complex path for water goes through, but water flies through very quickly. So when water is inside, these openings serve you as water capillaries. But when the material dries, in the absence of water, those spaces between two layers close and material becomes completely impermeable. So very strange material, impermeable to anything except for water. So this is kind of together with other phenomena. It's really very unusual. So I hope by those three simple examples I gave you an idea that the material is indeed quite unusual, and we still continue learning about this. So I'm a fundamental scientist. My duty is to provide engineers and application specialists in the fundamental knowledge, so they won't question what's happening with this material if they put it under one or another condition and try to utilize its properties. But people continue asking the same question: what about application? The material is so unusual. Okay, but it's for you boffins, you enjoy it, what it's good for me. So especially funding agencies and so when we will start getting our goodies out of this material, it has been already 10 years and we still do not have, I don't know, a graphene supercomputer or something like that. That's, my friends here asked me yesterday to tell you the story, okay, which I sometimes tell. It's a story about dolphins, okay. Once I was on a boat trip watching dolphins. I did swim with dolphins. I was born on the Black Sea coast, occasionally seen those dolphins in the sea. So it's a familiar animal, but at this boat trip about 10 years ago, it was something unusual happens. Dolphins came close to the boat and tried to play with humans. Okay, they wanted to be touched and coming around and allowed to touch them and show their eyes out of the water. I have never even read about something like that happening. 20 people, 20 customers on a boat. You can imagine how romantic this moment was, communication with nature, with a wild animal, not in the zoo at the sea. So it was a silence for, I don't know, 2 minutes. Everyone was mesmerized by the phenomenon, by this interaction with wild animals. And then suddenly in this silence, a little boy in behind shouts, "Man, can we eat them?" Look, nature provided us with this incredible experience of a new material which we were not aware that existed, say, 15 years ago. The material shows such a broad range of properties. We are still at this romantic moment trying to learn something new about the nature, about sort of materials which are one atom or one molecule thick, which we need not experienced before. Of course, funding agencies and governments shout at us, can we eat this material? Can we use it in agriculture or in computer sciences and etc.? Things comes, eventually will come. So there was an age of Bronze Age, then Iron Age, then Silicon Age, Plastic Age. All the progress of human beings is based around those materials. This is why we call those ages by the name of different materials. What happened quite recently, 10 years ago, that the nature dropped at our lap those materials which we were not aware that they exist. Graphene has many sisters and cousins which are, again, one atom and one atom thick. And whether you want it or you don't want it, you hate this material maybe, but it's inevitable. Now we know this material. We, as a human beings, will learn how to utilize materials. And this kind of materials, especially with these remarkable properties, eventually will end up in arsenal of what we use next to iron, next to silicon, next to aluminum and other materials. But obviously, when you're talking about superlatives, you can always think, what can you do with this material? If it's so unusual, can it be better than, say, silicon or better than aluminum and so on? Until, say, 6 years ago, I objected to discuss any application at all because there was no production of this material. Now there are few hundred of companies, probably more than that, around the world which can produce this material in square kilometers and in tons production. I think the smallest estimate it will be 1,000 times per year, mostly produced actually in China, but there is mass production of this material, so one can think about, speculate about this, its applications. So there are tens of thousands scientists around the world looking for applications of this material, so they came up probably with hundreds of thousands of different possible uses. You look through patent literature, there are more than 10,000 patents already filed, and the application ranges from, I don't know, new kind of transistors to DNA analysis, to batteries, to composite materials. Some of them are very far in future, but some of them, like batteries, improvement batteries, and composite materials, are already happening in different industrial labs around the world. Small, the material is not there is no graphene revolution. Yes, it's gradual diffusion of this material into different areas. People add this material into the batteries and get a few percent improvement, and they're happy with their slightly better car batteries. People put this material into tires, and the durability of tires increases, and it costs not that much as an additive. So people put this material inside in paint, protective paint, and decrease the price, surprisingly, of paint and improve its quality as well. So gradually applications are coming, but probably not as fast as governments would like to see. It's not a string of symbols you can write as a computer program, and in a short 2 years you become a billionaire if you're lucky. It's a material, it requires many decades to fully develop, but because of these remarkable properties, it's really a very fast progress, much faster than anyone could expect. I think I'll switch the gear and would not discuss what I'm doing now beyond graphene and go to my final transparency, which is aimed at mostly young generation of people who are in this audience. If you take a pencil and draw a line on a paper, you know what's happening. There is a pencil trace, and pencil trace consists of pieces of graphite which are within pencil lead. If you take a magnifying glass, you will see that flakes are not all the same. Like in this transparency with the Scotch tape, you see that some flakes come thick, some become thinner. But if you look carefully, it took several hours for me personally to find a monolayer, but monolayers are also within this pencil trace. So graphene within pencil traces have been literally in front of our eyes and under our noses for 500 years since we started using pencils, and no one noticed about this. So when I was PhD student and postdoc, I thought all physics has been done. But this story tells you that something sometimes very close to you, and we don't know that it exists though there. So there is a lot of things to remain to be discovered in the world around us, and this area of research in particular is very hot and moving very fast and shows no sign of being exhausted. So this Mackenzie Institute, McGrath Institute, which was opened yesterday, it's investment for the next 3-4 decades in future in this very hot area, and I congratulate this university to be at forefront of this research. And thank you very much for your attention. Thank you. Thank you.